Yeah, so my name is Revathy. I'm a postdoc in the Seismology and Geodesy division at the GI. I am from Kerala. It's a South Indian state in India. And now I live all the way across the globe in Fairbanks and work at the GI. Given this move, especially this temperature transition, there's one question I'm always asked, and that is why? And my answer to that has consistently been earthquakes. But what about earthquakes, though? So, when it comes to earthquakes, there are some primary concerns surrounding the likelihood of the where, the when, what to expect, the impact, future hazard. And to address these questions, one needs to study the cause, the mechanism, probable effects, interactions, and if there is a scope for early warning and rapid response. For this, we used mainly two tools, that is seismology and geodesy. And seismology is essentially the study of earthquakes and wave propagation. Traditionally, we use ground-based data for this. And geodesy is a study of the size, shape, geometry, gravity, etc., of Earth and other planets. But for now, we concern ourselves with Earth. And this mostly has satellite and ground-based data. So in this presentation, I'll mostly deal with how some of us at the GI try to understand the effects and interactions and rapid characterization of earthquakes for a couple of large earthquakes that have happened in Alaska in the last couple of years. So let's first look at the Alaskan plate boundary. Here we have the Pacific plate plunging beneath the North American plate. If there was no resistance between these two, basically the plates would just slide past one another like a well-oiled conveyor belt. But there is a lot of resistance. So this causes part of the interface to be stuck, and the eventual release is in the form of earthquakes. And this motion is detected by ground and satellite-based instruments. So in Alaska, along the Alaskan plate boundary, we had a couple of earthquakes in 2020 and then in the following year in 2021. Oh, in 2021, that is the 2020 Semyonov and 2021 Chignik earthquake. Now, these earthquakes occurred within a span of 1 year to one another, and they occurred in adjacent patches. This very fact that two large earthquakes occurred along this plate boundary in this span of time itself is a reason to look at this particular area because of the frequency, the magnitude, the variability of seismicity in this area. So let's first look at the Semyonov earthquake. Here we looked at seismic data, radar data, which Franz was talking about, GPS data, and together we came up with a fault model for this earthquake, which essentially tells you how the fault moved during the earthquake. Similarly, we came up with a fault model for the Chignik earthquake also. But given that these earthquakes occurred within 1 year and adjacent to one another, one important question was, are they connected to one another? Yeah. So for this, let's first consider a winch spring brick model to understand if these earthquakes are connected. So imagine a winch connected to two bricks that are, again, joined by springs. If you crank up the winch, what happens is there is a force exerted on the spring. Now, if this force is greater than the force that is holding the brick one in place, the brick moves. And if, because of this motion, it can exert a second force on brick two. We can compare this to the winch being the plate motion, the first brick being the Semyonov earthquake, and potentially brick two being the Chignik earthquake. So what we were trying to see was if the Chignik earthquake was connected to the Semyonov earthquake. So basically what we did was we used the model that we had come up with and then calculated the stresses on the plate boundary. The color bar over here shows you if there was a positive increase in stress or a negative increase, negative stress change. And here, the beach ball here and the star, I don't know if it's visible, but this is the location of your Chignik earthquake. And what we find was the Chignik earthquake occurred in a very clear patch of increased stress. So this answers our question of whether the Chignik earthquake was in fact triggered by the Simeonov earthquake, and by the results, it looks like it was. So the next question is, there are a lot of red patches in here. Does this mean all of these red patches will cause earthquakes? So we continue to look at GPS data from stations around this area, and we found that these stations continue to move way after the earthquakes occurred. So this means any increase in stress can either result in continued motion or result in an earthquake, or maybe a combination of both. So it depends. So it's very important to look at continued motion in a given earthquake-prone area to be ready for activity in the region. So far I've covered how earthquakes interact and what the effects of earthquakes are in the Alaskan plate boundary. But the next question is, can we use this data for immediate response right after an earthquake? So we basically use the same data, the seismic and geodetic data, to estimate earthquake magnitude and ground motion. But this is heavily dependent on what the station coverage is, and if there is data that is freely available, or if the data was cut off by the earthquake. So this motivated us to look at whether seismic and GPS data can be interchangeably used to arrive at the earthquake magnitude. So here is an example of co-located stations, that is seismic and GPS station at the same location for the Chignik earthquake. What we find is you find the same earthquake signature in both seismic and geodetic data. And this was hopeful for us because this means we can use them interchangeably to arrive at the earthquake magnitude, which is very similar when computed using both data, as well as ground motion estimate when the stations are interchanged. So to answer our own question, whether seismic and geodetic data can be interchangeably used, yes. But when it comes to seismology and geodesy, this is just a fraction of how it can be used. Like Franz and Victor mentioned earlier, this can be used for deformation along volcanoes, landslides, glaciers, a multitude of other deformation patterns across the globe. But I'm using this platform also to kind of call your attention to what we call the geodesy crisis, which is essentially over the past 2.5 decades, there's been a steady decline in people who work with GPS data. And this is a huge problem because it's like building a great house that we hope will last for several years and not having the infrastructure or personnel to deal with this data. So again, I'm encouraging students and supporters of science to continue supporting us, and hopefully we'll get more students. And this is a very predictable bait of field work that I was fortunate enough to do. And the places were so awesome that there's a fake photo in there because it's from a movie. Thank you.